Okay, perfect.
Now I want to give the floor to Laura Ricci. So we're very pleased having her here. So she did a lot of great work, both in community building, setting up conferences, and being editor of important journals in our field. So it's really great. She's professor at University of Pisa, and please, Laura.
Thank you very much. I thank you for inviting me. I am very happy to be here. And this is my group at the University of Pisa. We started since 2014, I mean in the Bitcoin era. there was only Bitcoin. I started together with Damiano Di Francesco Mahesa, who was very passionate. It was a cyberpunk guys, so he liked Bitcoin very much. And now I have this group, that you see, a big group of people, 5 permanent people, a lot of PhD students. We have also a national program, a national PhD program on blockchain, especially focused on blockchain in Italy. And these are some PhD students in that program. And we worked in several areas of blockchain. I will briefly summarize the area we are working on in the end part of my speech. But in this talk, I focus mainly on one of our contributions, that is a contribution in the field of access control. This is a joint work with CNR, Pisa, and we managed to bring access control on blockchain, so to build a system which is a blockchain-based access control system. What is access control? It is simply a set of techniques whose aim is to protect a resource and by defining the rules that has to be fulfilled by the users that are called subject in this area, by defining a set of policies. And the resources you see may be physical resources, file system, and so on, but maybe also smart contract. No? And this is, this is easiest because you are all inside the digital world. You don't go outside in the physical world. And in particular, in this work, we focus on attribute-based access control. Attribute-based access control is a methodology of access control that is based on attributes of users, of resources, and also of the environment. And the policies may refer these attributes. And we refer to a standard that is used in the ABAC community, that is XACML. It means Extensible Access Control Markup Language. And it is based on XML to define the policies. It is a very verbose formalism, okay, but we use that because it is a standard. It is also characterized by a reference architecture. You have this architecture for XACML, you have to define this component, and some of this component, we have brought some of this component on the blockchain before, and the basic component are this one, the PEP, that is the poll enforcement point, that is the component of the system that interact with the user, intercept the request from the user, and pass the request to the other part of the system, and then reply to the user, permit or deny. Then we have the PAP, that is the policy administration point that manages policies, retrieves the policies that are useful to take a decision. And there is the PIP, the policy information point, that interact with the sources of the attributes and with the environment to take the value of the attributes. No? And so here you have interfaces towards different systems that are the sources of the attributes. And then there is a PDP, that is the core of the system, that is the part of the system taking decision, takes the policy, and the value of the attribute and takes a decision. Our key idea is to bring this PDP to take the policies, the definition of the policy, and bring on in a smart contract. So have a tool that translate the policies into a Solidity smart contract and execute the logic of the decision on chain. Of course, the advantages are that it is the decision made by this system is rather opaque in the sense that you don't know if you have a centralized system, you don't know if it is the decision that the centralized system has taken is really the right decision, or simply you are not, the system does not like you and does not permit you to access the resources. So there is the auditability, of course, of the blockchain that is very good in this case. And we have published this a fast version of our system in this paper in 2019, and this is the architecture of the system. You have the entities are the subjects. The subjects are asking resources. The attribute managers and the resource owners. So the resource owners, there is that component that is called the PTP, that is a translation point that translates an XACML policy in a smart contract. Then you have the resources that may be off-chain resources or also smart contract that make request to that smart policies, and the smart policies take the value of the attribute from other smart contract. So in the first version of our work, also the value of the attributes were published on chain. And this is not good, of course, because of privacy. Everything is disclosed on chain. So this is the first idea, but we were aware that not all the value can be provided in clear on chain. And so we have improved in this paper the solution by supporting private attributes and using the technology that the previous speakers have already presented, that is zero knowledge and self-sovereign identity, trying to adhere to the self-sovereign identity paradigm. So we have used Socrates. I know that there are other tools like Circom, a lot of other, but just to fix the idea, we have used this tool. So in Socrates, you have to define your policy, your access controls policy, through a domain-specific language, typical of Socrates. Then you have the compilation, and you have the compiled output. And from the compiled output, with a trusted setup, you generate a verification key that is used to generate the verifier of the policy, and the proving key that has to be transmitted to the user, which, together with the input that the user wants to submit, that may be some public and some private input, generate a witness, and together with the proving key, the proof that has to submit to the verifier on chain. And and so what is the idea? The idea that it is that, first of all, the trust assumption, the attribute manager are trusted for us. Are like government entities releasing an ID, or universities releasing a degree, whatever you want. So they are trusted. And they provide a set of let us say, And this attribute manager manage the private attributes of the user, know the private attribute of the user, but do not disclose on chain the attributes. They define a set of predefined conditions on the attribute they manage, and they generate some zero-knowledge verifiers for this condition predefined. So, for instance, you have a university, you may have a zero-knowledge verifier that verifies that, I don't know, the average degree of a student is over a certain threshold. They are fixed, this verifier, and they put on the chain. So, they are published on the chain. The resource owners then you have the resource owner. We will have an example after. The resource owner must define the policies to access their resources. And they deploy smart contract to define the rule to access their resources. And this smart contract can refer the zero knowledge verifier that have been deployed on chain by the attribute managers. So the policies is done by the resource owner that refer the zero-knowledge verifier to verify some condition on the private attribute of the user. We have, for instance, let us suppose that there is a university, the university administration, that deploy on-chain a set of verifiers, like, for instance, the first one, as I said, check that the average grade of a student is over a threshold, another that the student is regularly enrolled, the average credit for years, condition on the private attribute they manage. And now suppose that the resource owner is, for instance, an educational program that, for instance, want to assign a prize, some prize to a student who have an average grade above a given threshold and has been enrolled in the university for no more than 3 years. So there is a smart policy that is deployed on-chain by the educational program refers the zero-knowledge verifier to verify this condition on the student that are defined on private attributes. The role of the subject at this point is the subject receives from the attribute manager a proving key, the proving key that has been generated by the attribute manager, and together with the attribute produce the proofs that is sent on chain. And the zero-knowledge proof is generated by in this case, the student on their premise off-chain, of course, and then sent to the verifier on-chain. Of course, we have a problem because a malicious student, malicious subject in general, can use attribute of their own, not the attribute that they have received by the zero-knowledge, by the attribute manager, but can build, in some sense, a fake proof. No? So we need a way to link the private attribute of the user to those that are really received from the attribute manager, in this case, from the university. This is an example. For instance, imagine you have the university. The university sends to the student the private attributes of Bob, but together it generates, we use hashing, basically. So it sends to the user a nonce, and then it computes an hash of the private attributes of Bob together with a nonce. And publish this on chain, commits the hash on chain. No? So for every attribute of Bob, there is another smart contract that stores the hash of the private attribute of Bob together a nonce that is that is generated for Bob. You can also generate more nonces. It depends from the or a nonce for a user or a nonce a different nonce for each request. These are possibilities. When Bob requires his prize, in the case of the example I made, he generates a proof and submits the proof to the verifier. So the verifier may be, the smart policies on chain may refer public attributes of Bob and also private attributes through the verifiers, to the zero-knowledge verifier that have been submitted from the resource owner. Let us see the overall architecture that is, you see, related to the use case I did before. There is the university, Bob, and the education facility. The education facility creates and deploys on-chain two smart contracts, the one that assigns the prize to the student if the conditions are met, so refers to a smart policy, and the smart policy refers to a set of zero-knowledge verifiers that are created and deployed by the university. Together, this AM contract, that is a smart contract storing the hashes that I previously described that connect the student to, that guarantee that the student is submitting a proof with the private attribute that he has really received from the university. Okay. I think that we have in the paper several experimental results. One of these is about the proving key and the circuit size that is generated by the toolbox, by Socrates, and as a function of the value checks. What are the value checks? The value checks are the basic checks that are done on the attributes. So a politics is an and/or of several value checks. No? So value checks are the, atomic condition that I am checking. And we have checked from 1 to 70 condition inside the policy. You see that for instance, 50 value checks, you have a big size for the, this is in megabyte, for the, this is from the proving key, that is 600 megabyte, and the circuit is very large, no? Is 5 giga. It is very, very, very big. But as far as concern access control system, consider that we have made this check, this proof, this experiment just to see how it scales on the number of value checks. But real policies that are used in real life have no more than 10 in general basic condition. It is very difficult to find a policy that has more than 10, even if we have checked. And furthermore, the proving key and the circuit has to be sent from the attribute manager to the user, to the student in this case, but only once. No? It is not repeated. It is needed to generate the proof. Then we have also made some experimental result on the gas that is spent by the smart contract. We have developed two versions of our system. One we have called monolithic, and the other modular. That means that in the modular version, we have a different verifier for each different basic condition. Instead, in the monolithic version, we have only one verifier for all that puts together all the conditions that I want to check. And of course, the monolithic is better. The monolithic is better, yes, sure, because you need only one smart contract, one call, and so on. Okay. And so this is one of the topics that we are investigating. But as I said, there are other works related to this topic that we have done and we have published and now we are doing. For instance, this is if you framework this work in the framework of self-sovereign identity, of course, the verifier, that is the resource owner, has to trust the attribute manager. This is the basic assumption. The attribute manager is trusted, gives attributes that are trusted. This may be the case or maybe not. So you can also define a system. You have defined the system that we call the multi-layer framework to evaluate trust. That is, in some sense, there is not an absolute trust, but there is we can call a web of trust. No? So a graph of trust relation. I say, okay, I have a friend, I trust that friend, and that friend say me that entity is really trusted. It's like a graph, no? A peer-to-peer graph that you use for evaluating the trust. We also are working to integrate fully the standard of SSI, the Web3 consortium standard, in our environment. So taking the politics written in XACML and trying to integrating in the fields that are free all the information that is useful for us. We have also other teams. Generally, we are working on layer 2 technology for blockchain, authenticated data structure. Of course, this was a proof of concept using Socrates, but we know there are other libraries. The problem with Socrates is a trusted setup, that you have the toxic waste, we know everything. And so we are looking for other alternatives. And and cross-chain technology in general. And another topic that is different, but we have a project on this, is also on the part of analysis of transactions taken from Bitcoin, Ethereum, for instance, taint analysis. There is a famous ransomware, and so the policy also in Italy is very interested to understand when someone pays for a ransomware in Bitcoin, to follow the flow of Bitcoin where they are going. It is not easy because it is pseudonymous, but it may be we have some result. And we have several projects, in particular 2 grants from the Ethereum Foundation. One is this cross-chain authenticated query, and this one has been just, we have applied, and we have just received the answer, that is authenticated and efficient interblock event queries on Ethereum. We have several Italian projects from the ministry, and PNR, Piano Nazionale Resistenza e Resilienza. These are money coming from Europe, that is again related to digital identity, self-sovereign identity, and things like that. Okay, this is all. Thank you for your attention.
Other questions to Laura? Oh, Ingo.
Hi, Ingo Weber from TU Munich. Sorry, you lost me somewhere between slide 14 and 15. In your presentation, you said that some attributes are kept private from somebody, but then you put hashes on the blockchain, and then somebody verifies the hashes by having access to the private attributes. So,
yes.
Who gets access to the private attributes, and what do you keep still anonymous there?
No, I mean the private attributes are kept private, and the only 2 entities that know the value of the private attribute are the resource owner, the attribute manager, that is the university, and the user, me, and not the resource owner. So how is this possible? Because in the zero-knowledge verifier that is deployed on-chain by the attribute manager, there is also a check inside checking that the user is presenting the hash, presenting the value of the nonce that corresponds to the hash that has been published on chain by the attribute manager. So the resource owner does not see anything because it is inside the verifier.
Okay.
Okay?
Thank you.
Okay.
Just because I mentioned it in my talk. So is there any, the question is there any plan to be able to authorize the people that can verify? In other words, maybe not here, maybe a university degree is relatively harmless, but for a lot of these attribute-based things, we really should have like something that says, okay, this entity is allowed to verify a certificate, and this entity is not. A particular example, so one of the W3C examples was that you could prove that you're employed when you're opening a bank account or renting, but a typical person doesn't move apartments very much or open bank accounts very much, and what they actually do a lot is apply for jobs. And if you can verify current employee, if a prospective employer can verify that you're currently employed, then they will discriminate against unemployed people.
Yeah, I think it is very interesting, and very interesting. And I think for the moment we have, I don't not more, in that paper that I discussed, the multi-layer trust framework, we have some notion of distributing, no? Because it is no more reasonable to have those verifiers that are government entities, no, and only predefined, like we are in my young days. I was used to, no, but you need. An approach that is more peer-to-peer distributed. We are trying to do that, but we have not implemented nothing for the moment. Thank you very much.
Thanks a lot for the question. My name is Prabhakaran from Siemens. I would like to ask a question regarding this property that you translate from one language to another language and then writing the policies in Solidity. Have you investigated from the access control perspective, safety and liveness, kind of nothing bad can happen with multiple attribute-based access control policies in the modular version that you mentioned? Is there a possibility that combination of multiple attributes can lead to an unintended side effect and getting access?
Lead to, sorry?
Unintended side effect.
No, we don't. For the moment, our focus was bringing the things on the blockchain. No? So there is a simple translator from the XACML policy to the smart contract for simple policies. So we have not focused on the topics of translating and checking. This may be also interesting, but it is very interesting for me because I take the suggestion and bring home.
Thank you.